our great pleasure today to welcome Andrea, who will talk about practical solar spaces on thinking.
The pleasure is greater for me to be here again and give a talk give a talk in person. I gave a talk, remember, 4 years ago, but it was COVID time, remote. A lot of friends, the audience, and so especially from Séminaire, who one year ago provoked this study. I will not tell you the beginning of the story. If somebody is interested, I will tell after the the subject of the talk are, as I said, solar spaces, fractional solar spaces of food. So we look at the behavior of Gagliardo seminorms. Gagliardo seminorm is a double integral, omega times omega. Well, just look at the quadratic case. Everything can be done on any P. This is 2s, 2bx. So this is well known. It's the Gagliardo seminorm in HS of omega, and omega is a subset of Rd in the diagonal. You know, this is a kind of interpolation between H1 and H2. We suppose that the functions are in L2. So H1 and L2. So HS omega is in L2. In S is between 0. And in a sense, this is an approximation or a discretization of the Dirichlet. So this is a kind of difference quotient with a weight which is given by the rest of the integral. Okay, and we look at the spatial in a special situation when this omega is a thin film. So omega is instead omega epsilon. So this is epsilon here. And this is a small omega time 0 epsilon, where omega, small omega, is an open set. So let's say it's bounded open set in R dimension. So now we are happy because we had a small parameter, and when there is a small parameter, maybe we will set to 0. We are very happy, me and Francois, people. And so we would like to understand what happens when epsilon varies, if epsilon tends to 0. It's a very simple question. So it's that we can make a parallel in the case of H1. So in H1, everything is so clear. It's the starting point of nonlinear theories, and I have all the names of the Raoult here. And so let's recall how do we start in the H1 case. So in the H1 case, so this is something like the gradient of U squared dx. This is the H1. So we say, okay, but we are worried because here we have an epsilon. Let's make this epsilon disappear. And so we change variables. We say, okay, for U, we define D. So U V of X. Now we have to introduce some notation. So X prime are points in Rd minus 1. And then you have an XD. And this is U of X prime. So X prime remains the same, epsilon X. So the domain is V of V is omega, small omega times 0. So we have fixed domain. So, and here we write this as 1 over epsilon, the integral of the omega, this omega here. The vertical gradient plus epsilon, the horizontal gradient. So I put a prime thinking of the d minus 1 dimension. Okay? Square, of course. And from this, you can pass to the limit in a sense. So this tells you that, oh, sorry, this is V. This is V. This tells you, okay, that if you divide, well, first of all, if you multiply by epsilon, you get the vertical, the vertical direction. You get functions which are maybe in L2 because you're looking at functions in L2 with a distributional vertical derivative which is in L2. For the rest, we don't do it. Nothing is implied by this first part. And then when you inside divide by epsilon, if you divide by epsilon, this has to go to 0. So you get something which has no vertical direction.
So the function b does not depend on epsilon?
No. Okay. This v will depend on epsilon, say. Okay. Then, okay, I'm not doing. You will have a sequence of the epsilon. This will give you some bound on this v epsilon. This v epsilon will converge weakly, depending on when weakly either in L2, maybe if you have a bound in L2 and you're looking and you're multiplying by epsilon, or weakly in H1 if you are dividing. But the fact is that okay, this is so. This is the way how can say if I take if I divide by epsilon, I take 1 over epsilon gradient u square dx. In particular, this well, if I divide by epsilon and let epsilon goes to 0, this will imply that the derivative is 0. This vertical derivative is 0. So this v depends only on the horizon. So in a sense, we say that this converges to integral of omega of this. So this means that if we have a sequence for which this function is bounded, the relativity epsilon weakly converge in H1 of the enlarged of the scale set, something which is independent. So we have a dimension reduction. So we have this. So we have so that v epsilon converts to some v, and this v is indeed v only of x prime. So we say that here we have dimension reduction. We should put an LJLL, so be more appropriate. Okay, so this is our scheme, which is very, very simple. Let's try to put it here. But now here would mean we're scaling v, but now we are messing up this kernel here. If we scale v, we scale u to v, this kernel is not a kernel of the Gallardo seminorm anymore, because you are scaling in epsilon. This variable will I erase the variable, the vertical variable. Okay. So the questions here. So it's not so simple as this. This is really on my group of models. So our questions are now. So what are the scalings? So the scalings which take the place of 1 over epsilon. This is not clear at all if you look just. The second, do we have dimension reduction? And then what is the limit? Say gamma limit. In this case, these are gamma limits, meaning that we can let any sequence converge, and then we will have compactness theorems that will ensure that the limit is dimensionally reduced. But actually, the real computation are pointwise. Will be pointwise when the limit is dimensionally reduced. So let's look at the first scaling. So first scaling. So the one that replaces 1 over x. So in this case, let's introduce some notation. This is as epsilon of u. So the first scaling, we do some heuristics. So now we take the semi-norm, and then so the heuristics means that we assume that the limit. So we take this as a model. So this model means that we are only interested in what happens on the vertical direction. So we take u, which is u of xd, which means that the v is v of epsilon xd. So now here we can first, we can have an interval 0 epsilon, 0 epsilon. Now we separated the vertical and the horizontal direction. Here you have v of ux minus u of u of x minus uy squared, which since depends only on the vertical direction, we can integrate afterwards. And here we have a double integral of 1 over x minus y d plus 2s dx prime, dx prime, dx t, dy t. So we have to understand how this kernel behaves. And you can do this by scaling. And so somehow you scale one of the two variables, the other one you keep unscaled, and this will give you in dimension d minus 1, we will give you an epsilon d minus 1, you scale it by epsilon. This will give you an epsilon squared when you want to scale to 1. And okay, you are scaling this one in such a way that it scales as a whole, and you get an epsilon to the d plus 2s. This is hand waving, but somehow you do some numerology here, and you see that this goes when you scale it like epsilon to the 1 minus 2s, and then you have a double integral 0, 1, 0, 1 in terms of v, and when you change variables here, you get so this is in v, dxd minus vyd squared, and you get an xd minus yd 1 plus 2s. This comes from part of this and part of from the Jacobian. Okay, I'm not going to all the computation. d, and with epsilon goes to 0, you get also an integral r d minus 1, which is 1 plus c to the square d plus s. This. Okay. So this gives you the scaling. So the first scaling that replaces 1 over epsilon is epsilon to the 1 minus 2s. So it depends on s. And here it also suggests what will be the gamma limit. So if we do the pointwise and divide by epsilon to 1 minus s, here you get the Gallardo seminorm, the S Gallardo seminorm in one direction, in the vertical direction, integrated. So here there is also some measure of omega coming from one of the integrations here. So is the Gallardo integrated on omega prime times a constant. And this constant is interesting because it suggests that these kind of constants govern the change of variables in these Gallardo seminorms. So this is a hypergeometric integral. Let's call it CDS. But it depends only on DNS. So the gamma limit, actually, in this case, is, well, there is no compactness here. So you have to assume something. So you take the gamma limit in the weaker two topology, because you have control only in the vertical direction, which is ensured, for example, if you have boundary data. So in this L2 weak topology, meaning what is mean? This is you're taking the weak topologies of this V, the two topologies for this V, you have then 1 over epsilon, 1 minus 2s is f epsilon s of u converge. Exactly, you divide this by epsilon. Here, the integral on omega is just, this omega is the integral of omega of v of x prime. So let's write it. This is the introduction. We use this notation for the Gallardo seminorm. This is squared of the Gallardo seminorm in omega epsilon. This is the vertical Gallardo seminorm square of 0,1. And then you integrate this prime. So somehow, here, instead of 1 over epsilon, you get something which depends on s. Well, that's fair. And here, instead of having the vertical, so here you can also rewrite this as the vertical grade Dirichlet integral, you get the vertical Gallardo seminorm. So this times epsilon to the 1 minus 2s replaces this part here in a formal development, which can be seen as a gamma development in a proper sense. But we have found the first scaling. So the first scaling is epsilon to the 1 minus. Now, well, given that this scale, and I unfortunately erased what I'm going to rewrite, I have to evoke another well-known theory, the one by Bourget, Brzezinski, and Mironescu. this is a way to better specify how this Gallardo semi-norm interpolates between the L2 and the H1, and especially, particularly close to 1. So we have that if you normalize this Gallardo semi-norm, so, and this is, you take the square of this on some fixed omega in Rd, so in this case, omega is in Rd. Okay, this pointwise on H1 and then also gamma converges. Of course, we are interested in a pointwise convergence, but more or less they prove the gamma converges already there. So this, as epsilon tends to 1, converges to something very precisely described, the Dirichlet integral in Rd, where here sigma d is the d-1 dimensional measure of the sphere in Rd. Now, this implies, okay, that we have computed the gamma limit of these energies. So the gamma limit of these energies was the integral on omega of the S semi-norm here, x prime. Now, if you multiply by y minus s, this part here, well, here it's written that converges. So, and we take, sorry, this is 0, 1, x prime. This converges to pi. Okay. So the new so going to dimension. So one dimension. Sorry, this is 1, 2, 1. So this converges to the integral of grade v, grade x squared. So we are applying the this Mironescu in 1 dimension when omega is 0, 1. So somehow we see that this Mironescu result tell us that when your epsilon goes to 1, if you scale by y minus s, you reobtain this term here, s goes 1. Sure. So in this case, this analysis commutes with this s tending to 1. We look at the dimension reduction regimes. But take note of this theorem. We're going to use it or have it as so the dimension reduction regime. So now, again, we take the Mironescu approach and look deeper in the proof. So the idea of Mironescu is, okay, I look at this omega times omega. Well, actually, first of all, I see that it's not necessary to look at all the points, but the points with certain distance. So x minus y less than some r, which may depend on s. Actually, it's just important that it's much larger than 1 minus s. So we can discard everything that happens outside because of the integrability conditions that infinity of this curve. And So you have ux. Well, now let me rewrite this, changing variables. So you x plus psi minus u of x, c squared, and here we have psi. So I just changed the variable x minus y is psi to the d plus 2x. The psi x. So x, we can think of varying here, and here we have this VR of 0. Here, this pole, which says that the interaction must be closer than less than. And so the idea is then, well, that if, for example, u is Lipschitz, this is less than psi squared, then you use the integrability. This is like this goes like the measure of omega, and then you have to integrate VR 1 over psi d plus 2s minus 2 in psi, and this will give you a contribution which is of order. Well, this is of order. Well, we don't care actually, but we this is of order. So we get an integral of 1 divided by 1 minus s, which explain why you have the 1 minus s in front. So the idea now is look at what happens in small balls. So let's do this also for string fields. So we have this string field. This is epsilon. There is some x here. And we look at small ball centered in x. Well, small ball with respect to some parameters less than 1, but we have two cases. So so we are looking at some ball BR. It depends if R is less than epsilon. So if R is less than epsilon, we have both here. So here is d-dimensional. Or epsilon here, we have a ball which is not much larger, but say R larger than 2 epsilon, or larger than epsilon. Then you have an x here and y. We are looking, sorry, what happens outside this ball. So we have balls. We are looking what happens here and what happens outside balls of the same of the radius of this radius. So we look at this slightly larger ball. We will not lose much. But here, if r is larger than epsilon, then the distance between x and y is comparable with the distance between x prime and y prime. So this is a d minus 1 dimensional case. So this is a d minus 1 dimensional integral. So when you're looking at this, you have, in the first case, when you're looking at the integral at this, so you have, here you have omega epsilon, this will give some epsilon. Because omega epsilon is 1 dimension epsilon. And here, in the first case, you have an integral on, say, the epsilon. Because you are over the epsilon. If it were 2 epsilon, it would be the same computation. Okay. As long as this is the Lipschitz function. And in the second case, you have something like small omega epsilon minus this b epsilon. But this you can do in small omega minus the d minus 1 ball or this epsilon, because essentially it's d minus 1 dimensional. So it's computation. So here you compute this, and it's epsilon to the 3 minus 2s divided by y minus s. Something, if you want to keep everything that depends on epsilon and s, and not constants which are depending on the dimension, then you get this. If you have this, well, there are two cases. This is interesting because you are integrating on RD minus 1. So it depends on the integrability of this kernel in D minus 1. Well, not of this kernel, but of this kernel in D minus 1, which depends whether you are lower or higher than 1/2. If S is lower and higher than 1/2. So you have this integral here. So the contribution outside a small ball are of epsilon squared if S is less than 1/2, and still epsilon 3 minus 2S, not divided by 1 minus S, if S is larger than 1/2. In the case S equal 1/2, these two exponents coincide. And this is a critical case because the contribution inside and outside are the same order, and we have to be more careful. But no, this is also, we can put the equal sign in both or in neither of them. So we see a strange situation that the suggested scaling depends on S and has two forms, whether S is larger or lower than 1/2. So let's look at what happens. Here is the definition. The question we remember, and we will make it. So this is what we call the low integrability or low differentiability, I don't know, the regime. This is the high integrability or yes derivatives or Gallardo integrals. So let's look at the low integrability regime. Okay. Then we have a lemma, which we can state like this, which was more or less just seen before. So that was given for a function, assuming that it was only depending on the vertical direction. Here if you it says that okay, u minus t minus u of x prime yd. So we are freezing one horizontal. So this is a kind of Fubini argument. We are looking what happens in a vertical direction, freezing a horizontal. So it's a one-dimensional section. It's d minus yd, d plus 1 plus 2s. So it's the one-dimensional s. That is h d yd dx prime. This is less than a constant than the semi-mod. Let's write it as epsilon. Okay. So this okay. And we saw that this one, if you change the variables, we have seen that this thing here is epsilon to the 1 minus 2s, epsilon minus 2s, the corresponding integral times a constant, which was the hypergeometric integral. So we get, this means that if we have a bound sufficient bound on this, you get a bound on the vertical, on this vertical. So this implies compactness. So if in particular this divided by epsilon to the 1 minus 2 tends to 0, which is a particular case of this regime here, then you get compactness. So this is a corollary of this. This is compactness in weekend 2. So it says that if you have a bound on 1 over epsilon squared, our functionals, then up to addition of constants. Here, everything is invariant by the addition of constants. We just look at differences. So I don't mention it. Then the corresponding the epsilon converge weakly in a 2 sum D, okay, which depends on an X prime. So we have the dimensional reduction. So if we have a bound of our energy divided by S squared, and we are in the regime S between 0 and 1/2, then you get weak compactness from this. Okay, is a consequence of this partial Fubini theorem, which is one-sided Fubini theorem, and the whole Fubini theorem is two-sided. So with the optimal constant is not known. If you're looking at, for example, the book of Leone, who does all the computation of this, this is not optimally stable. And theorem in this case is gamma limit, which implies an increase of integrability or differentiability. Depends on how you read this result. So it tells you that 1 over epsilon squared, this so this semi-norm, so this we call Fs epsilon mu, this converges with respect to the weak to topology to nothing else than the semi-norm S plus 1/2. So you have an increase of 1/2 in the integrability on. So this limit depends, is dimensionally reduced, so it lives in omega. The limit is still non-local, and it is a Gagliardo semi-norm, which is an increase of 1/2. This is not surprising. And let's just do this proof, because it can explain also something if one is interested in the question of François Murat after the end of the talk on thin films. So we have to follow the. So we have this omega epsilon here. And then we have a sequence, but it's not important that you have a sequence. You can just look at one function, x minus y squared, which now we know in the limit will depend on an x prime. So it's x prime. And here it's x minus y squared. And then you have 1 over epsilon squared. 2 plus 2s. dx dy. Now, one thing that one can say, okay, I'm worried about this x minus y here because it behaves badly close to the diagonal. I cannot control the x minus y with x prime minus prime close to the diagonal. But let's just throw away the diagonal. So let's take it when x minus y, x prime minus prime, is larger than that. Of course, you have a lower bound. Our energies are larger than this one. Okay. But now, if you are on this set, the vertical part is of order epsilon, while the horizontal part is of order a fixed delta, and epsilon goes to 0. So the vertical part is negligible. So you can put x prime. Okay. Now you don't have any dependence on the vertical direction anymore. So you can just integrate out omega omega. You have 0, 1, 0, 1, which cancels on epsilon squared. So you get an inequality with this one. Well, now delta has no reason to be there. So you let delta go to 0, and this disappears. But here it's written something different. Oh, sorry, it's written something different because we have D. Yeah. No, it's written the same thing because here this is t minus 1 plus 1 plus 2s, which is d minus 1, the dimension of omega, plus twice s plus 1/2. So it's the s plus 1/2 semi-norm in the d minus 1 dimension. So have to, well, the extreme cases, let's look at what happens. We can let S depend also on epsilon. There is no reason why here epsilon S, in my proof, which was half the proof, but it's indeed all the proof there, it's there is no dependence on epsilon. So we can let S epsilon. But you can also let epsilon go to 0. So here, as epsilon going to 0, usually it's bad because you have some interaction that go farther and farther. There is a theorem of Manzia-Shaposhnikova about this. But we are not in this case because the limit is just you get the 1/2 norm squared. So that's instead as epsilon goes to 1/2, which is the upper limit, then s plus 1/2 tends to 1. So we can apply the, well, no, that's not true. Let epsilon go to 0 with fixed s, and then let s tends to 1. So the limit is this one, but s plus 1/2 tends to 1. And so this, if you multiply s plus 1/2, u s plus 1/2, this is the Bourgain-Bridges-Mironescu result. This tends to the integral prime square dx on omega times some precise constant d minus 1. So this suggests that from 1/2 onwards, and I have to do this in 5 minutes, you get something. So I go fast in this. So the high integrability regime So in the high integrability regime, compactness is complicated. because you want also the limit to be in H1. And you cannot use the compactness of Bulgarian-Mironescu, but because they don't have it. But of Pons, who then prove the compactness result. Because the spirit is that you integrate on small balls fixed radius, or you take a convolution with a fixed convolutional kernel, and then you let the kernel tend to 0. But this is incompatible of having a small epsilon. Okay. But you can go around this and prove a strong compactness. Compactness, we have the dimension reduction compactness in L2. Well, to be precise, with L2 strong of omega times 0,1 to something which is in H1 also only. So the limit is in H1. And we have we have the gamma limit. So the limit then, so you remember now that the scaling was epsilon to the 3 minus 2s. And you take this fs, whatever, as epsilon. The gamma limit then is, well, the space now, the limit space does not depend on S. It's always H1. Well, in a sense, it must be, it cannot grow larger than S1 because by the Bulgarian-Mironescu's results, we know that in the case S equals 1, it will be H1. So we have this converges to be precise, 1 minus S, ASD, and then you have the Dirichlet integral of the limit in dimensionally reduced. And this kernel here is another type where it has a normalization constant here, b minus 1, and you have another hypergeometric B2, sticks out. Hypergeometric constant. This hypergeometric constant, then you can relate with the gamma function. If you ask ChatGPT, he will do the job, or it takes a long time to figure out. Okay, and okay, you can do also the case where you scale this. You choose S epsilon. S equals S epsilon, and you let you multiply by 1 minus S, so you take the singular limit of this, and this tends exactly to what, so to the constant of Bulgarian-Mironescu time the Dirichlet integral. So this is a commutation result. So it tells that if you go to, if you first take in this regime squared, if you take first the Bulgarian-Mironescu limit and then let epsilon go to 0, it's the same as doing the converse. So whatever S velocity of S epsilon you have, you always converge to something of the same form. Until 2 days ago, there was an open case, but Margherita Soce, who sits in the last row there, has given me the solution. So the singular case, so when S is equal to 1/2, you have some kind of invariance by scaling of some part of the energy. And you know that when you have this kind of invariance, you better scale by logarithm. So that's the scaling of vortices and other problems that are scale invariant. And in this case, so if you fix S equal to 1/2, this converges to the d-1 dimensional constant of Bourgain-Brugis-Leonescu, and then so in the case you have these two singular regimes at S, because it's not you just not divide by 1 over epsilon to S. You have to divide to multiply by something which tends to 0 at both ends, and which interpolate between the d-dimensional and d-1 dimensional Bourgain-Brugis-Leonescu. So, well, I think this is all. And I think it was, for me, it was amazing. It is a really simply stated problem. You take this and you want to let epsilon to 0, and it has a rather complex and also with some open question. For example, the role of these hypergeometric kernels and possible proof of a Fubini type, the deduction of the right scaling for a Fubini type theorem in fractional spaces, and okay. Well, there is a last thing. The last thing that
in the last line, this is power S for the seminorm on the left.
oh, sorry. This, of course, it's always two. Sorry, I'm always talking in a hurry. So the last remark on this is that one can look at this development and ask, as S tends to 1, is this development compatible with this process? And this is so is if epsilon to the 1 minus S tends to 1. If epsilon tends to minus S tends to 1, then you have the same taking the first order and the second order gamma limit with the proper scaling. They coincide with this one with okay, with in front this constant here, which must be there. But this is the scaling which somehow answers the question of Francois. And that's all. Thank you.
Another question?
Yeah, I don't understand the singular case. Is it the same object as the one in the gamma limit when you take S equal 1/2? Or
no, when you so when you take S different from 1/2 and let S tends to 1/2, then this goes to infinity, because you have to divide by something which tends to infinity. This tends to infinity as S plus 1/2. So somehow to describe, actually, there is a little thing that I swept under the carpet, that we have not looked at the case when S epsilon tends to 1/2. When S epsilon tends to 1/2, it tends in a way which interpolates between S minus 1/2 and 1 over log epsilon. But this is not so uncommon. For example, in phase transitions, in this fractional phase transition, you have the same case. You S orbital 1/2 is singular, and then apparently there is a very strange singularity because you pass from one behavior to another one with a jump, but there is no jump actually. There is a continuum.
Okay, my question is even much simpler. The weight in front of it are completely different. You know, you have 1/epsilon squared log epsilon, and the other one for S equal 1/2 is 1/epsilon. So that's a different regime, or you see?
No, we have not treated the case.
Here you have S larger than 1/2.
Larger than 1/2, yes.
So 1/2 is a limit case.
1/2 is a limit case, but it blows up.
Why?
Because of this. You have to look at the integrability of this. Or you have to write this as a gamma functions, and then you see what happens. Yeah. Sorry. There was not evident.
I don't have a good question.
Yeah.
But I remember when S is equal to 1/2, some people use the lifting of adding one dimension to get use the Jerry-Kahneman operator to this kind of technique. I think I'm not sure. I'm not an expert, but this was used by Caparelli, Vasseur, and so essentially you expand the dimension by 1.
Okay.
And then so today it's not non-local anymore.
Yeah.
Sure.
No. This is really a direct.
Yeah, also that.
Okay, I think what it means is that it allows to go back to traditional gradient numbers for epsilon half. You see your omega epsilon as the boundary of something.
Yes, really
one like
sure.
Even for other tests, the way you want to do it.
But you're having boundary operating with also variance factors. That is really something.
So here you can see the gamma convergence, and in the conventional is convex. Somehow one can deal with smooth functions somehow.
Sorry.
So here you can see the gamma convergence.
Yes.
And the conventional epsilon S is convex. Convex. And so somehow we can go with smooth function. And so my question is that what happened for the pointwise convergence? So if you
Pointwise convergence.
so you take a function u depend on x prime.
X prime, yes. No, yeah, everything is.
Yeah, I know that, but if you take the limit of the functional when u depend only on x prime, and what happens?
No, they converge to the core is the pointwise convergence. So the convergence is. So the gamma convergence means the pointwise convergence is stable. This is not always like that. So there are regimes here where you have.
Did not lie the lim sub and lim thing, something like that for gamma conversion.
Yes. So, but the lim sup is achieved by the trivial sequence. U is equal to U. But you cannot go lower with something which depends slightly on the vertical direction.
Okay, just another question. So what happened if you mix a little bit the behavior? What happened for x prime? What happened for xd? Here somehow you have two regimes, just for xd and for x prime. And now I don't know with how what is the way for epsilon. You can see that kind what is the power for x prime or for xd. But I want to see the missing phenomenon between x prime and xd in the limit.
Well, then you have to take another function. No, it's just like in the case of the ring. If you scale by epsilon here, you multiply by epsilon, everything that happens on the horizontal direction disappears. It's weights epsilon. If you divide by epsilon, then this must be 0, and so. But as such, you have to change the weights here to get both.
Somehow you assume that you had the super disqualified line, but you change the way you assume the super another quantity.
No, it's
So for them, you can see that the weak case. So for them here, you assume that the 1 over epsilon square u epsilon s. And now u epsilon
okay.
is,
You can assume whatever you want, but this is the regime where you see this gamma limit. Otherwise, the regimes intermediate are trivial. So in the intermediate, so if you take an epsilon here, which is between epsilon and 1 over epsilon, okay, this will be 0 and this will be 0. The same. So it's and the other one will explode. I mean, so that's you will get a function which is 0 and plus infinity, depending whether you are in the domain or not, or outside the domain of the next limit. So that's but this is general question about limits. Then you can find.
You? I have one question. What was François' question?
Good question. Okay, but then you have to spend
No, in 1 minute.
in 1 minute. Okay, so but I have to okay. So the question is this one. So we have the Bouguin-Brugis-Mironescu result. Even in 1 dimension, say 1 minus 2s. So 0, 1 to 0, 1, dx dy. And this we know that it converges the integral of u prime square times the constant. Now take some coefficients. So it's a quadratic homogenization. It's quadratic form, it's homogenization. Okay. Now you fix S and compute the limit. Now, if you fix S and compute the limit, and go back to the proof that I said, you have to remember this to understand the part of the question. If this converges to 1 minus S, so if you let epsilon goes to 0, and here you get the average, let's call it A bar. This is the average of A. It's not the harmonic mean. And then you can let this, you use the Bouguin-Brugis-Mironescu and you get this constant in front. But if you let these tens first let S tends to 0 formally, and also you get this. And you get something which is different. So this tends to constant times a bar u prime square. This tends to constant a lower bar, which is the harmonic mean. So you can get the average, the harmonic mean, which are different. So the question, the suggestion of François was, you have to look at what happens in small sets, in sets of size epsilon here. Sets of size epsilon are thin films. That's how we looked at it. And the answer is not known. So what happens in general is not known, but we would like to make some, well, you know, what happens in general inside here. But here we know that this happens when epsilon to the y minus s tends to 1. So that was somehow part of it. So we don't know the whole picture. So we know that here this happens when epsilon minus s tends to 1, and this happens when one minus s is much smaller yeah, is much smaller than epsilon squared. So there is a gap. So here is 1 minus s, much larger than 1 over log t. So there is a gap. But still, in this regime here, we know that if these are optimal, then it's very strange to pass from one of the other. So you take S epsilon in this regime, what happens? That's and it's a linear, quadratic question, so it should be easy.
Thank you again.